Moving forward, we're going to go ahead and talk about some maximum oxygen consumption. So this is a VO2max concept, or what people like to call aerobic capacity. So I really wanted to begin with a quote from Steve Prefontaine, who's one of the great American endurance runners over the last few decades. And he talks about how a lot of people run a race to see who's the fastest, but he likes to do it to see who has the most guts. And what he means by that is you can push yourself into exhausting pace and then at the end punish himself even more, right? So you believe you hit your limit, but there's always a little threshold that you may be able to go beyond. This is that concept of max, and whether there is a true VO2 max, or whether there is a true threshold of pain and endurance that we can hit. Now, before we get into the discussion of oxygen consumption, and how the body uses the oxygen, we first need to talk about gas exchange. And we acquire the oxygen from the atmosphere, right? So it's important to understand that the chemical makeup or the concentration of chemicals within the air atmosphere doesn't really change that much. There are a few places and a few times where it will change a little here and there, but for the most part, it's pressure of the atmosphere, pressure difference between the body and the air, making it more difficult for us to inhale large quantities of air. And this is, in general, the major reason why we have problems at altitude. But we will talk about that a little later. Um, but to go further, here are a couple of schematics that illustrate the process of delivering this oxygen to the tissues of the body that are in need. It all begins with the inhale of the atmosphere. Um, the air then travels to the lungs of the body. There are numerous capillaries that surround the lungs. These capillaries are rich in carbon dioxide and they're low in oxygen, right? So the rich in carbon dioxide because they carry back the byproduct to the lungs from the mitochondria during that ATP creation. Um, it is a site here where there's the exchange of O2 and CO2 from the capillaries in the lungs. So CO2 travels into the lungs to be exhaled, and O2 travels into the bloodstream fluid to be delivered to the body. Within the blood, there's a high concentration of hemoglobin. Now, hemoglobin has a high affinity for the oxygen, and it serves as a carrier and a transport to oxygen for the cells of the body. The transported oxygen is then delivered to the mitochondria of the cells, and this is again where it creates energy in the form of ATP as needed. Now, it's important to understand that during exercise, the majority of the oxygen that comes into the body is then transported to the working skeletal muscles, right? So the energy required of the working skeletal muscles, this can increase up to about 20 times normal. The blood vessels that lead to the working skeletal muscle dilate, and it allows for the greater amount of oxygen flow, increasing that delivery of O2. Carbon dioxide is produced here again as the byproduct of ATP and delivered back to the lungs for removal. Um, it's also important to note that during exercise, blood flow to um, organs and non-working skeletal muscles is shunted. So it does bring majority of the oxygen flow to those working muscles. So if you are simply doing a cyclopedometer, most of it's going to your upper body and your arms. So next we want to talk about the idea that work requires energy, and then energy creation of energy also requires energy, right? So the first principle of exercise physiology is this concept of work requires energy. But in order to maintain that specific work rate or velocity of movement over a long distance, the ATP must be supplied to the cross bridges as fast as it is used. This is seen in a sports exercise physiology book. But in the body, we have these stores of chemical energy that are waiting to be converted. Um, there are a couple pathways, that we can go over, and we'll go over those later on. But there's aerobic and anaerobic. For our purposes and the majority of this topic, we deal with the aerobic pathways, and then it all converts it to mechanical energy, that movement energy. Um, Mechanical energy, for those that don't know, are more the kinetic energy and potential energy. but in this case, kinetic because you're actually doing some movement. So oxygen consumption, well, what is it? Bruce Gladen reports oxygen consumption is a direct indicator of the energy that's supplied through oxidative phosphorylation. But simply put, oxygen consumption is the amount of oxygen that you inspire minus that you've expired. So the difference there is the amount that you've consumed, right? So if I have a certain amount of food on my plate and I eat a certain amount of it, what's left, I've consumed amount that's gone, right? So that's what that essentially is saying. Now, some key components to this that we'll talk about is cardiac output. That is what Q is. Oftentimes you'll see a dot over the Q or dot over certain one of these ideas. Oftentimes the V as well. Certain things, but that simply means the rate of, right? So cardiac output is your heart rate times your stroke volume, and stroke volume is a volume per beat, and it's end diastolic volume versus end systolic volume, and we'll get into a little bit of that later. And then you have the arterial mixed venous O2 difference, or you also see it called just arterial venous O2 difference, and that's that AVO2, and that's the amount of oxygen that's taken up by the blood in one trip around the system. Okay. Cardiac output represents the systemic blood flow, while the AVO2 diff represents the systematic oxygen that's extracted during this portion. Oxygen consumption is proportional to the intensity of exercise. So as intensity of exercise increases, so too is the consumption of oxygen. Oftentimes because you have a heart rate or a higher a need for the muscles to consume some of that oxygen. So how do we measure oxygen consumption? You'll see a gentleman here running a test. But we'll talk about the Fick equation, and that's a huge equation there for you. Or not huge, it's not huge, but in size, but it's huge in what it does and what it means. Your oxygen consumption is the product of that cardiac output that we talked about on the previous and that AVO2 difference. So those two multiplied together give us what your cost is at that workload or that work rate. So an increase in either your oxygen consumption is due to either the cardiac output or the exchange of oxygen through the AVO system. The greatest effect of increase is seen, although through your cardiac output, and we'll talk a bit more about that in a few slides, but that's where most is seen. But your VO2 represents the rate of which this oxygen is utilized. And it's generally reported normalized to body weight. And that's where you see this ml per kg per min is normalized to body weight. And what that does, it allows us to compare man versus woman, or a 6 foot, 240-pound man to a 5'9", 5'8", 160-pound man, right? Because what this does is it know that body size is an attributes to the amount of the rate of oxygen that you use. So in order to normalize this, we have to compare. We have to normalize it to body weight. So that's why we do this. So if you see it in liters per minute, it's not normalized. But if you see ml per kg per minute, you know that's normalized to body weight, and we can go ahead and compare. Now, the important complex for this presentation is this last one. That's the VO2max count, right? So this is the maximum amount of oxygen or rates of oxygen that you can utilize in a exercise setting. So as that work rate increases, this is your limits, the top you can go. And it's said to be reached when both cardiac output and the arterial venous oxygen difference are at their max, right? So if one's not at the max, then you're really not at your max. You have a little bit more you can do. So here's just a couple quotes that I've taken from different books, all relating to what their ideas are of maximum oxygen uptake, or VO2 max. And essentially, it's just VO2 max is thought to be closely related to the functional capacity of the cardiovascular system and its ability to deliver oxygen, right, to the working skeletal muscles during dynamic work via the blood, right? So the important aspect of this is it's a dynamic exercise. It's often incorporating large muscle groups, and a good portion of your body weight supported. I don't. I want to go before we go any further. I just want to quick touch on the historical perspective of this, because there is a lot of controversy surrounding the ideas of VO2 max, where they started, but also now where they're going and what it actually is in the body that does this. But A.V. Hill and Lupton are the first that are known to measure oxygen consumption during exercise back in 1923. Um, an interesting thing for them, though, they theorized from their findings. I didn't share you this graph with you, but you can look at the graph if you want. Um, that there was a universal VO2 max at 4 liters per minute, um, and then with any intensities above this, we shifted to another metabolism, with anaerobic metabolism. Um, this value corresponds to something like a 13 kilometer per hour, and was a moment of shifting from that aerobic to anaerobic metabolism. But they didn't include any individual differences in theory, so they thought it was across the board. All humans had this 4 liter per minute difference. And then 1955, Henry Longstreet Taylor, who was an American um, physiologist, came by, and then they actually went back and looked at some of the Hill and Lupton work, and they're like, oh no, their research actually shows this linear trend, and then there's some sort of plateau phenomenon. So they were looking at the previous research, not even conducting any of theirs, but we're looking at some of the previous stuff and concluded that. Um, so this goes to kind of goes to the line as a lot. What I've been talking about is science is a matter of interpretation, right? And so I would argue that they interpreted Hill and Lupton stuff incorrectly, but this concept of a plateau phenomenon, and what that is you can see there on the top, as your work rate or workload increases, the amount of oxygen that your body is taking in no longer increases. It's interesting that this is a graph that's related to the Hill and Lupton, because you see that plateau happening at the 4 liters per minute. And you'll see the submaximal workloads there listed too. And those are all their linear trend that's going up. But this plateau is a point just prior to the maximum workload that's achieved, and then the oxygen remains the same. But the athlete is able to work slightly harder without taking in any additional oxygen. And we'll talk about one of the big controversy about this a little bit later. But this concept also brought in that, or Taylor and his colleagues also brought into their theory that this is something that needs to be measured in the lab, and there may be some individual differences um, within this value, or so it may not be the 4 liters per minute at this time, and they recognize that there are individual differences. So let's go ahead and go a little further and talk about some of the factors that affect your oxygen consumption and your VO2 max. A major one is age, and there has been shown to be a gradual decline of up to 9% per decade following 25 years. Age-related changes are thought to be due to reduced contractility, efficiency, and fatigue resistance of the heart and skeletal muscles. So these become less active and less vibrant as you get older. Um, but there has been shown to be a decrease in this drop with exercise. So through the increase or the continuation of exercise following those later years, you can decrease the decline by as much as 5%, which is killer. Women have been shown to have a lower VO2 max than their male counterparts. It has been theorized that this is due possibly because of the increased body fat content. There's a reduced muscle size, and or a less power, or they have less powerful muscles. Um, it's going to be interesting to see if this continues in the future. Um, Now that women are becoming more and more involved in athletics over the last few decades, and maybe they'll catch up to their male counterparts in the long run through training and evolution. But the range at which fitness and training programs increase VO2 can be up to 60%, right? So I put here fitness and training shows a running program on average of 5 to 15% increase. But this ranges from 0 to some people up to 60. The training effect has a lot to do with your pre-training fitness level. So the more fit you are, you're going to be limited on how much you can improve. But if you're somebody who's untrained and not fit, you can drastically improve your VO2 max. And this one right here is one of those ones that really draws it a line. Is there that genetic component? So what is the genetic ceiling, if there is one? And if you are already trained, are you closer to that ceiling? Therefore, you only get that 0 to 5% increase. And then you have the altitude, right? And so altitude is a big effect. It's a mostly dramatic effect on the max values. Um, and this effect begins at 1,200 meters. And then there's a decrease of about 10%, 3,000 meters of elevation increase. And again, we talked about this earlier, but it's the barometric pressure reduction of the air that reduces the pressure gradient between the atmosphere and the body that the diaphragm can make. That is responsible for that air intake. Some reports say that there is a change at certain levels and certain peaks in the air composition. But for general purposes, we're going to discuss the barometric pressure reduction and these changes in the pressure gradient. But just to put it in your mind, so the average mountaineer, people who climb mountains, records a max of 15 mLs per kg per minute, which is about 27% of their sea level values. So there's quite a drastic drop. And you put it into more perspective, you must have a 9 ml per kg to maintain life. So it's pretty close to being minimal, which is interesting. So let's talk some about the limiting factors for your VO2 max. There's essentially the limiting factors are the rate at which O2 is transported to the tissues. You have oxygen carrying capacity of the blood and the amount of oxygen extracted from the blood. And all these are broken up as the pulmonary diffusing capacities, the maximum cardiac output, oxygen capacity capacity, and the skeletal muscle. All right, so the skeletal muscle, that's where you interact, where you're pulling out the oxygen from the blood. The oxygen carrying capacity, that's the increase in hemoglobin in the blood, which also then increases the amount of oxygen carried. This is the idea of blood doping, right? EPO. That will say Lance Armstrong and let you hear this mostly in cycling, but you can hear it. You can use it in others as well. But cyclers are known mostly for it. The maximum cardiac output. This is probably the one that is most associated with these increases, and it's some. And Hill in this group said 70 to 85% of the limitation of VO2 max is seen in this cardiac output. In the diffusing capacities, there's a decreased transit time, which elites have that higher cardiac output. So that's one of those areas that the elites differ from non-elites in the ability to get the oxygen through the pulmonary area or the lung area. So let's talk a little bit about how we create or how we measure somebody's VO2 max. And what I put here is 4 pictures that depict different modes of transport relative to different athletes that we would use. You have a runner, cycler, a rower, and a wheelchair-bound Paralympic athlete. All 4 of these are perfect mechanisms that we can measure VO2 max, and they're all relative to the mode of exercise or athletic endeavor that each one of these athletes are used to. One thing I want to point out is in the running one there, you'll see the person, the researcher holding on or keeping the person upright, and the person is looking like they're bending over, getting ready. They're pretty close to failure, and that's essentially what we want to do is we want to push these athletes to to failure. We call it exertion, volitional exertion, to where they're just ready to collapse, but they step off or fall. Um, Most athletes or most individuals that conduct these should be puking, falling over, grasping, and really, really fatigued when they're done with this in the amount because they reach such a high exertion level. But to talk about the testing criteria here, it must incorporate about 50% of your body weight um, throughout the exercise. There must be a rhythmical and continuous exercise mode. So none of the repeated sprint bouts or fartleks or anything like that for a prolonged period of time. So as you like in the graded exercise test, we gradually increase everything, but it's a continuous. You don't stop to increase to the next level. It must be independent of motivation. You'll often hear people motivating people to continue, but that's only because you're trying to push through a mechanism. The motivation is you shouldn't have something you're trying to hit to compare you to another athlete. It should be just go till you stop or till you can't go anymore. There should be no time or numbers that people are seeing. And that's why often everything is blacked out. They can't see speed, they can't see heart rate, they can't see the values themselves. Only the researcher can. And they must reach a max capacity. So this is where the oxygen consumption plateau concept comes into effect. But as you'll see here in a little bit, not everybody reaches this plateau for numerous reasons, but not everybody will reach it. I found that quite a few people in a recent study I did didn't reach that. And if you don't reach a few of these criteria that are coming up, then we call it a VO2 peak rather than a VO2 max. VO2 max, you have to hit certain criteria. If you don't hit that criteria, then we just call it a peak value that you achieved. There must be standard conditions. That means that there should be no adverse environmental conditions. You must not put one of those hyperbaric masks on or do something that's trying to restrict any of the environmental conditions. Now with these blue, these are some of the individual criteria that people have placed on these tests to say, okay, this person reached a peak value or this person reached the max value. Um, we People use a combination of a few of these or one or two or all of them to validate their peak or their VO2 max reaching. The RPE, for those that don't know, is rate of perceived exertion. And this is a self-reported mechanism that relates to the relative fatigue of the individual. There's a high correlation to actual exhaustion levels. So we use this so when people are getting up to the 18 and 19, we know that they're reaching that portion where we need to keep an eye on them because they're about done with the test. RER, which is respiratory exchange ratio, is that ratio of rate of oxygen and rate of carbon dioxide consumption. And that is a measure of the intensity of work. And we do that by a range of 0.7 to 1 and then greater than 1, as you can see here. But a 0.7 is low intensity, burning majority of 100% actually of fat as a substrate. I don't know if I buy into that 100%, but that's what that's what everybody says, and that's what the books say. And then 1 is 100% carbohydrate or strictly anaerobic style intensity levels. I use a 1.15, and I think that's the UNLV criteria, but here it's at least a 1.1, which if I rate, if I reduce mine to 1.1, I had more people hit VO2 peak or VO2 max than VO2 peaks because between the 0.1 and 0.15, it's a big difference as more tests you do. Another measure is blood lactate. This one's a little bit more difficult to measure. You need to have some kind of blood measurement, finger prick, anticubital. Some universities now are starting to toy with a disposable tattoo. It's a lactate sweat tattoo that you can use that indicates a little bit of the blood lactate levels. There's also another one I saw today that's a strap that you put on. They look kind of like a sock guard that measures lactate of the calf. And then you have peak heart rate. Once your heart rate reaches similar to the age predicted maximal heart rate, they say that could be a classification as well. I'm hesitant to use heart rate for my stuff only because I know that I work at my intensity is at a high heart rate majority of the time, especially because I drink a fair amount of caffeine, so that adds to my heart rate, my resting heart rate. Now let's go ahead and break it on down and talk about some stroke volume, which is the difference between end diastolic and systolic volume. Or as an increased stroke volume, you have an increased preload, increased contractility, and afterload. So first, let's break down the EDV or the preload, and that's the end diastolic volume. So preload basically is the volume of blood on deck. So it's a volume sitting inside that ventricle. Now, stroke volume increases steadily until about 25 to 50% of your VO2 max. The plasma volume increases um, 200 to 300 milliliters, causing a 4% increase in the VO2 max. Now, a loss of volume during detraining. Now, this is the number one cause of a reduced VO2 max. So that plasma volume, and there's a few mechanisms that keep plasma volume up, which we won't go too much in this, but it's shunting again blood and fluid away from non-working systems and environments to what needs to be done. But this Frank-Starling effect is that the ventricle stretch mechanism that allows a greater amount of fluid to be drawn in um, and pushed out. And this is through the increase in cardiac fibers, aiding in the force of contraction, which increases the volume of the blood pump per contraction. So this Frank-Starling mechanism increases the contractile force, which then pushes and creates a harder flow of blood coming out of the ventricle. And then there's an increased venous return, and that is amount of blood coming back to the ventricles, and it goes underneath a greater filling time because your heart's not beating as rapid. It allows it to fill up to its maximal load. Now let's talk about contractility, and this is basically the strength of the cardiac muscle to contract. It is increased, but it's directly affected by the end diastolic volume, heart rate, and afterload. So a lot of textbooks won't even include this part into it because it hasn't been proven to the level of its expectation or its um, product. Generally speaking, it hides itself within all the other three that are components of it. Now, the final component that aids to an increased stroke volume is that of the afterload. And actually, it's a reduction in the afterload or the total peripheral resistance. What does that mean? Well, that means it's a reduced resistance to the ejection of the blood from the ventricle through the aorta. Um, Trained muscles do provide less resistance to this flow during maximal work. The decrease that's seen in this resistance is not due to traditionally thought local factors associated with endurance training at high work rates. For example, the hydrogen, carbon dioxide, like those type of things. But rather, it's a reduction in the sympathetic vasoconstrictor activity of the arterioles within these muscles. Um, this happens because what you have here is you have an increased preload, you have the increased contractility, so now you have a higher volume, greater force, and the resistance to this um, uh, ejection is reduced. So now you have a greater volume going at a higher work rate through something that's less reduced. So this is increasing that stroke volume. Now, the main goal of the blood flow is actually to maintain blood pressure through the sympathetic vasomotor behavior. So it's not to get blood flow where it needs to be, but they need this blood pressure to be maintained through vasoconstriction and vasodilation. This is one of the reasons why you'll have certain mountaineers who can do better than others at higher altitude, and that's because they have a better ability to maintain this blood pressure through vasomotor, sympathetic vasomotor behavior than others. Some have more and more problems as they climb the higher mountains, and some can do it without oxygen. And this is because of this ability, not because their partial pressure handle it better, but they can maintain the pressure throughout their system that helps exchange oxygen throughout their body where it's needed. And then to finish up, we're going to talk about the AVO2 difference, so the difference between the arterial and venous oxygen content, right? So this is the increased ability of the muscle to extract oxygen following training through increased capillary density accommodates the increase in blood flow. The rate of blood flow is also decreased, increase in the amount of time for diffusion, and then you see an increase in mitochondrial density, which also increases the ability to extract oxygen within the blood. So all of this AVO2 difference shows how through the blood flow, these increased capillaries and mitochondria can actually increase the amount of oxygen that's taken out of the blood. So therefore, from the arterial to the venous, that difference is greater. Now, let's talk about the truth, right? So, some of the controversy, and a lot of this comes with Tim Noakes and his lore of running. And again, there's people who buy into it and people who don't. I'm one of those that tends to buy into it because um, all these things people have been reporting and believing have been shown up more and more to not be true. But this plateau phenomenon, it's only found in about 30 to 50% of the tested participants. Some say it's found higher in percentage of athletes because they're used to going to that threshold, where untrained individuals don't reach the threshold. I actually buy into that too. I think the more apt you are at pushing your boundaries and limits, the more apt you are at that plateau phenomenon. But I do not think that it occurs in all people. Tim Noakes talks about um, the ability or the lack thereof of your body to allow it to go to 100% anaerobic. Now, what does that mean, right? So if you go into 100% anaerobic, you are not utilizing oxygen. Well, your heart does not function and beat without oxygen. And the capillaries that surround your heart cannot work anaerobically. So his concept, Tim Noakes' theory is, well, if I use all the oxygen and I'm no longer being able to utilize the oxygen, my heart's going to stop beating. It's going to become ischemic. It's going to die. So therefore, there has to be mechanisms, and you'll see the cardiovascular and central governor models there. Those are his mechanisms that are based off of your body protecting itself from going to 100% anaerobic. So the theories are based on blood flow and oxygen transport, limiting the ability to injure tissues and organs of the body. So this is some stuff we'll talk about in class, but it's pretty exciting. It's pretty interesting. This is where you can get some good debates. And then, so what I listed here is these are some of endurance athletes, and you can see their VO2 max values on the right, the big table, ranging from 85, which is the highest, all the way down to 69.7. These are all elite athletes. You can see the reference there and then the major performances. But table 2.2 is where we're going to start the controversy for next week and talk about people's VO2 max values. But then we're going to talk about their marathon times and their fastest marathon times. And Jean Bonnet, who has the highest VO2 max value, does not have the fastest marathon time, right? So this is that concept of VO2 max is a great predictor of aerobic capacity, but not necessarily the best predictor of athletic ability, right? So this is your performance concept in your upper limit, but not every you can't always go and achieve that for a long distance, and there's many other factors that play a role. So that'll bring us into next week. But focus on the components of endurance and exercise activity that are going to enhance your VO2 max for this session. Thanks for listening, and we'll come back and talk about running economy next time.